Good morning, everyone. My fellow over here introduced us, so we're from MIS Systems, and we're going to be talking about real-time aggregation system that we built at MIS Systems. So just to give you an overview of what exactly MIST is about, and what data are we talking about. So MIST is a company in the networking world. We are bringing AI and machine learning to Wi-Fi industry in the sense that we want to detect problems in your Wi-Fi. Like this place has a bunch of access points all over the building, and we want to detect if any one of you is having trouble with your Wi-Fi. So basically anomaly detection, and then trying to attribute what is causing that problem. But the focus over here would be how do we absorb all that data and what do we do with it. So you can see in this picture we get a lot of telemetry data from the access points that we have deployed all over the world, and we also do a second part of our business is doing indoor locations. So there are two sources that we get data from. The first one is getting telemetry data from access points. The second one is some raw data coming from the SDK that runs on mobile devices through which we do indoor location. And all of this data gets put onto Kafka over here. And that's basically the starting point. So once we have gathered all the data in Kafka, there are two compute platforms that we use. Most of the real-time processing that we do, it happens in Apache Storm. And some of the real-time processing, which I'm going to be talking about, and which is the topic for this talk, it happens inside Mesos. And just to put some context, because we're going to be talking and emphasizing a lot about reliability in this talk. 80% of our production data center runs on Amazon's Spot instances. For those of you who are not familiar with it, Amazon offers different type of contracts, and this is the contract where they do not guarantee about the server, and the servers can just go without much notice. I think they give you a 2-minute notice, but basically it's a very volatile environment to live in, and it comes at a significantly cheaper price. The savings that you can get is typically it ranges from 70% compared to the reserve instances. But what that means is that you need to make a reliable software. And so basically we get data in Kafka. There are the two compute engines that we use. We do different kinds of things over here, anomaly detection and aggregation and all sorts of things. And then that data goes into eventually goes into the databases that we use. Most of our time series data is in Cassandra. We use Redis for caching some key data, as well as Postgres for some configuration related data. We are a group of a lot of people, but these are the main contributors to live aggregators. Amarinder Singh Bindra, he leads most of the operations and daily work for live aggregators, as well as coming up with a new functionality in it. And Jitinder and Ibrahim, they've been writing different types of aggregations, because you can come up and write your own aggregations in live aggregators. And here's how the talk would be organized. So we'll first go over what exactly do we aggregate, and give you an idea of what aggregations we are doing. We're then going to talk about the overall architecture of live aggregators, and then a significant part of live aggregators, something which distinguishes it from a lot of other real-time processing systems, is its auto-scaling. And then we're going to talk about how we are using multi-level aggregations using Kafka to basically scale live aggregators in a reliable way. So I'm going to give Chunky the mic to come and talk about the next part.
Good afternoon, guys. So let me first start with a game. So I have hundreds of balls over here in a basket, and I want to count how many balls are over there of each color. So what I'm going to do is I'm going to ask one of you to come towards the basket and throw the ball one by one to me. That would be a very easy task, because I'm a good catcher. I can count it one by one. But what if I ask each and every one of you in this room to come towards the basket and throw the ball to me? I would do exactly what this guy is doing over there. I would save myself. So doing counting or any aggregation at scale is not easy. So at Mist, we have built a system which does aggregation at scale. And that system is Live Aggregators. So Live Aggregator is a distributed system which does processing and aggregation in real time. By the way, there is no basket, so you don't have to throw any ball. OK, so let's see how it works. So over here, you are seeing a total of 9 different messages coming in for a period of 17 minutes. And the message contains message ID or offset, client name, the bytes transferred by the client, and which organization or org ID the client belongs to. You can also see the snapshots of config which says my aggregations grouping key would be org ID or the organization. And what I want to aggregate on is number of clients. I want to find out the unique clients. And I also want to do aggregation on total bytes transferred. And I want to do the sum of all bytes transferred for that org. So let's take a step back. Let's process these messages one by one and see how this view or how Live Aggregator is creating the state which you are seeing on the bottom right. So at time t equal to 0, a first message comes in from user Sam, bytes transferred 100, and from org Mist. So the view would create and state that number of unique clients now for Mist is 1 and bytes transferred 100. And now at time t equal to 1, a second message comes in, but this time this is from organization home. So this is a different grouping key. So there will be another entry in the config, another entry in the table, number of unique clients 1, bytes transferred 60. At t equal to 4, third message comes in, but this is the second message for org Mist. And this is not from Sam. This is a different user. So now the unique number of clients are 2. Similarly, with fourth message, second message for home, unique client. So number of unique clients are now 2. So throughout this processing, this view did a total of 8 aggregation operations. For each message, it did one operation for calculating unique and second operation for doing the sum. And this view kept 2 time series, one for org home and another for org Mist. So before going into details, let me first briefly explain to you what the terms are, what terms we will be using throughout this presentation. So a view is basically a continuously running aggregator whose grouping column and aggregation info is defined by the user. A grouping column is basically a grouping key or aggregation key. And aggregation info gives you 2 information. 1, on which dimension you want to do the aggregation on. And 2, what type of aggregation you want to do. So in Live Aggregator, we support more than 20 aggregation types. And these are basically from the contributions of data scientists or developers, as Osman mentioned, that they continuously add aggregation types based on their requirement. And a time series is a series of data points coming in time order for a grouping column. So this is a high-level architectural diagram of Live Aggregators. It starts with a user comes in and says, I want to run this aggregation, push the config. When the config is deployed to production, it goes to Zookeeper. And when it goes to Zookeeper, the scheduler finds out, OK, I have this new view, or this view I have to schedule. It fetches those view from the Zookeeper, puts them in an LA task, and then throws it on the Mesos cluster. So all the LA tasks are running on Mesos cluster. And each LA task or each view, they are consuming data from Kafka partition. And since we are running the whole cluster on AWS Spot instances, which means any instance can be taken away by AWS at any point of time. So the memory state or the view state which we saw in the last slide, each view is keeping that memory state into S3 as checkpoint. And for monitoring and alerting purposes, we are emitting data to SignalFX. Once the aggregation is done for that time interval, each view writes the data to Cassandra. Cassandra is our main data store, but we also write to Kafka, S3, and SignalFX. That depends on what the user has defined in the config and its use case. And finally, it's the controller's responsibility to monitor that each view is running. If any view is not running from last 1 minute, 2 minutes, any configured minutes, then it is the controller who will alert so that we can page on call. So now let's zoom in and talk about live aggregator executor or LA task. So it does multiprocessing. Its main process, which is process 1 over there, it spawns multiple processes to do various tasks. So the very first thing LA task would do after getting deployed on Mesos cluster, it fetches the config of all the views it has to run. And then it spawns one process each for individual views. And it figures out which Kafka partition these views needs the data from. And then it also spawns one process for shared memory manager. And shared memory manager is the one who would share the message which is being read from Kafka with all the views. So let's see how it works. So first a message comes in, it is being read by Kafka reader, then being shared or being sent to shared memory manager. And then shared memory manager will just share that message, put that message into message queue of all the view runners it is running. Let's try to understand with real-time message coming in. I have this message 1, it is being read by Kafka reader, then being sent to shared memory manager. And shared memory manager would now copy that or put that message in each individual view runner's message queue. Once the message reaches the message queue of each view runner, now the actual work starts. Now all the views starts the processing. Let's assume in this case, view runner 1 is doing the aggregation which we saw in our last case, and view number 2 is just calculating the maximum bytes transferred in the org. So view number 1 would update the state as we saw earlier, and view number 2 will just keep the maximum bytes transferred for the org. In this case, it was missed, and message 1 was having 100 bytes transferred. Now let's see when a second message comes in, similarly read by Kafka reader, sent to shared memory manager, and then being put to message queue of both the view runners. And again, the view updates the state. View 1 updated and view 2, it also updated, but since the message transferred byte of message 2 was 60, so it kept 100 as maximum bytes transferred. So along with processing all these messages, each view runner is sending data to Zookeeper. It is telling Zookeeper that what was the last offset I processed, what was the last time I processed any message, what was the time of last message which I processed, so and various other informations. And this view state, which each view is keeping in memory, as I was mentioning earlier, we are checkpointing, or each view is checkpointing that state into S3. And once the aggregation is done, for that time interval, the view would just put the data to Cassandra. And there are 3 main reasons. One for alerting and monitoring, we are sending data to SignalFX, and we are also sending data to SignalFX for resource utilization. Each process resources, we are sending it to SignalFX. Oh, where is my executor? Okay, as I was mentioning earlier, we are running on EC2 spot. So any executor can be gone at any point of time because of the instance loss. So in this case also, the view which they kept all the data in memory and everything, it is gone. So we have to be fault tolerant. And we need to be prepared for failures like these. So let's see what the view or live aggregator would do in case we lose the executor or we lose multiple executors. So now there is no view. View is not updating Zookeeper that where am I when I process the last message. So the controller figures out, okay, these views are not updating anything, so we have to reschedule those views. It updates Zookeeper, and then scheduler finds out, okay, I have these new views or these views which needs to be rescheduled. Scheduler picks those messages, put them in LA task, and throws it out to Mesos cluster. So for simplicity, let's assume those 2 views are again scheduled in one LA task. They can be scheduled in multiple LA tasks, but let's assume for simplicity in this example. So now, when the LA task starts, the main process would spawn again multiple processes, process 2 for shared memory manager and 3 or 4 for view runner. But now, the very first thing each view runner process would do before even reading any message from Kafka, it would check S3. the view runners would check if there is any checkpoint available in S3, and if there is, then it would fetch that checkpoint from S3 and load it into the memory. And now the Kafka reader of this executor would read from message 3. So it is not reading message 1 and 2 again. So in this case, we are not duplicating message read from Kafka, and we are not duplicating the aggregation each view is doing. So one main thing to notice over here is that checkpointing is the key to recover from failure. So now you might be thinking, like, there might be one question in your mind is, why we are doing multiprocessing in this executor? Because multiprocessing doesn't come cheap. It comes with complexity. It comes with engineering effort, maintenance. So there are two reasons we are doing multiprocessing over here. One, we do not want each view to read message directly from Kafka. We want to share a message which is being read from Kafka by multiple views. One of the main reasons for that is, since LA is a very Kafka read heavy, we want to avoid reading everything from Kafka. And the second reason, which is the main reason, is we want to collect the resource utilization metrics for each process over here, for each individual view, so that we can do better resource management and auto scale, which Osman will talk about it later. Now let's see. Now let's take a look at scheduler. So a scheduler is a lightweight component of our system. We have implemented it to just do one simple task of scheduling views with minimal possible constraints. So let's see how it works. So there are 3 views in Zookeeper, view 1, view 2, view 3. They are in waiting state. So schedulers, Zookeeper manager, figures them out and picks those views, put them in the message queue, update the state that they are now picked. Once it is in message view queue of scheduler, the task manager of it would pull those views, put them in an LA task, and then schedules it on Mesos cluster. Once it starts running, they would update the Zookeeper state that now I am running. So there are 2 constraints which scheduler or task manager needs to follow over here. One, we do not want views consuming from multiple Kafka partitions to be in same LA task. For the reason we saw in last slide, we want to share the message which we are reading in LA task to be shared with all the views. And the second constraint is how many views the scheduler needs to put in LA task. And that depends on how many resources the scheduler has received from Mesos and how many resources each individual view would need to start execution. So the resource management part of it will be covered later by Osman. So now let's talk about some numbers. Now let's take a look at the scale Live Aggregator is running on. So Live Aggregator in total is consuming around 480,000 messages per second from Kafka. These are the messages read by all the Kafka readers across all the LA tasks. And the other number which you are seeing of 680,000 messages per second, this would have been the number of messages read by Live Aggregator if each individual view reads from Kafka. So you can see over here, we are saving more than 30% of network out on our Kafka cluster by sharing that message with all the views. So in our earlier example, we saw there were 2 time series and 8 aggregation operations. But in total, Live Aggregator is keeping more than 300 million time series, and it is doing millions of aggregation operations at peak time. And since each view keeps the state in memory, so across all the LA tasks, we are keeping more than 2.5 terabytes of data in memory, and they are writing billions of messages to Cassandra. So now Osman will talk about how we have been scaling from last 2 years and how we will continue to scale in next years coming.
Okay, cool. So, so I don't think anyone is going to disagree with that. Any distributed system in current day and age, it needs to be cost-effective, reliable, and scalable. And the reason that cost effectiveness and reliability is even more important in our context because we run on spot instances. Just to give you some perspective, how many of you have used or know about Chaos Monkey from Netflix? Okay, good. A lot of people have done it. So actually, I've been in my previous work, we were using it as well, and it was, for me, it was very inspirational because that was the first time I saw people voluntarily terminating machines. And I said, okay, that's the way to do it, because if your developers or your feature writers, they say that what I'm writing is fault tolerant, then you better test it out. And you shouldn't be scared of testing it out. And that was a great step towards this thing which is evolving, chaos engineering. And but one thing I noticed a few years later when we were using it was when we'd have problems, we'd stop. The first thing we do is stop Chaos Monkey, and I call it as controlled chaos. That you control your chaos. And for me, chaos by definition should be uncontrolled. You should not be able to stop it. Well, it turns out that Amazon's spot instances, they turn out to be exactly what I've been hoping for. Well, they save you money. They save you significant amount of money. I mean, typically, compared to on-demand machines, that you'd save around 85% for your Amazon cost. And similarly, for reserved, over-reserved, they'll probably save you around 70%. But the reason that I like using spot instances is that you cannot control them. It depends on Amazon users. It depends on external factors, just like a stock market. You're a small part of it, but you cannot dictate the price of a stock. Similarly, when you're part of the spot market, you cannot dictate the terms unless you're a major player, which we are not. But what that forces you to do is to be able to handle uncontrolled chaos. Machines can go away, and you have to be able to cope with it. And just to give you some idea, Amazon does a very good job of controlling that chaos, but you'll have bad days in the spot market. Like, for example, recently, I think this is from the month of March, we would have around, we went up to like 800 spot instances terminating over a period of day. And that's like more than the entire data center, our production data center. So the good thing about here was that I generated this graph after the fact, which means we didn't know that this happened. No one noticed, and that's because the way we have architected our system. But it's good to have spot instances, just because when my developer comes in and says this thing is reliable, we use spot instances on staging as well as a production environment. We catch a lot of problems on staging before things make out to production. But coming back to the real-time processing and all that, how do we measure that live aggregators is scaling well and it's doing what it's supposed to be? For most real-time applications, you measure how far behind they are from real-time, which is we call it lag, and that's basically the difference between the most recent timestamp that was produced to Kafka and the timestamp of the most recent message that your consumer consumed. So like, for example, in this case, I'm taking these 4 messages as example, and for the 4th message, the lag is 0 because that was the most recently produced message. If your most recent message consumed was number 3, then you're lagging by 5 seconds, and similarly. So keeping that in mind, let's see what happens when one of the, and this is production data from maybe a few months ago. So one of the spot instances terminated at around 10 o'clock. And as you can expect, the lag started to go up, which means that you're staying back far from the real time. And at around 10:15, the scheduler figures out that, okay, this view is not running. It reschedules it into another spot machine, and then you see this sudden jump in the lag. Well, that's basically the new machine coming up, the new executor or LA task coming up, restoring the checkpoint from S3, which is 10 minutes old, and that's why you see the lag going up from around 4 minutes to 10 minutes in all of a sudden. But once the executor gets scheduled, it clears the lag pretty quickly, and it continues processing from there. We are a startup, and our load has been, it's good for us that our load has been increasing significantly. We have been through quarters where we have more than doubled. So it's very important for us to truly auto scale. I don't want people to sit over there and keep managing, let's increase the resources in Mesos and all that. And this is a depiction of a load. And the interesting part over here is we of course have a trend, which is a healthy startup would have the trend, but something which a healthy startup can do without is the daily seasonality, as typically people in data science call it. We have a peak in the load in the mornings, another peak in the evening. So we would, while we were solving the auto scaling problem, we need to make sure that we not only cover for trend, we can also do auto scaling for the daily seasonalities. And what does that really mean? What that means is your containers should be right sized. So this cat over here is a container, and you're trying to fit in that container into that box. And she's obviously not going to fit in there. What you can do is you can give it a bigger machine or a bigger box, and then she will fit into it, but you're wasting all the space. So what's the solution? You find the right size for the right size box for this cat. How do you know that? How can you find the right size for this cat? The only way to do that is you should first know what is the size of the cat. So in other words, before you can right size your containers, you need to know how much resources your containers need. And one thing that, one figure that, on this figure that Chunky showed earlier, one thing we didn't cover over there was the resource manager part. So the resource manager runs inside every container of live aggregators. It's using psutil to grab the CPU memory usage of each of these containers, and we measure the CPU memory requirements of each of the sub-processes inside each LA task. So we know how much resources, how many cores, and for simplicity reasons, I'll be talking only in terms of cores. Of course, there are other dimensions to resources, but just to keep things simple. So for example, this view requires 0.8 cores. This view requires 0.6 cores, and then there is, because you are distributing messages between these different processes, you need to pay that cost in the shared memory manager. The more sub-processes you have to distribute the messages to, the higher the cost for the shared memory manager is, and that's why we measure it on a per view basis. Similarly, the cost for reading from Kafka is, in this example, is 0.2 cores, and that's the table, that's a snapshot which gets recorded into Zookeeper. So whenever the scheduler schedules, it'll keep those numbers into consideration. So let's go through a quick example. So Mesos offers us two cores to live aggregator scheduler. The scheduler has these three views that it needs to schedule. It says, okay, I need to consume Kafka stream, so let me dedicate 0.2 cores for it. The next thing is, let's take one of the views, and we have to allocate 0.8 cores for it, and 0.1 cores because the cost of distributing these messages per view is 0.1, so it attributes that cost to it, so we're left with 0.9 cores. We take the next view, which requires 0.6 cores, and now we are left with 0.2 cores, which means that view 3 cannot be scheduled this time. So what the scheduler does is it says, I'm done scheduling these views. Let's launch this container onto Mesos. And the interesting, the thing to keep in mind is that when the scheduler is doing that, it's of course, it got an offer of 2 cores from Mesos. It's leaving the remaining 0.2 cores, and it's just consuming 1.8 cores from it. So now we know the size of the cat. The next part is, what do we do with it? when these containers are running on Mesos, like like we saw earlier, it's a dynamic workload. It changes every day. It changes hour by hour. So we need to keep track of what is the actual usage over the course of the day. And during evening we have low load. So let's say in total from the previous example, I'm using 1.8 cores in this case, and I reserved 1.8 cores as well, which means that I have the exact right box for this cat. So lying factor is a metric that we use, which is basically number of cores reserved minus number of cores actually used. So in this case, the lying factor is 0. But when the load comes in the morning, the actual usage of cores for the container goes up from 1.8 to 2.2. But the container is still reserved, when it started, it reserved 1.8 cores. So basically, in this case, you are lying that you'll need 1.8 cores. You're actually using 2.2 cores. So the lying factor in this case is minus 0.4. And just to summarize all of this, if given the lying factor for every container, there are two thresholds that you can define. If the lying factor is negative, then you are causing problems. The cat is not fitting into the box. If the lying factor is a high positive number, then you're giving the cat too big a box, and you can save some resources over there. These are production numbers, and we run probably over 1,000 containers for live aggregators on Mesos today, and these are the lying factors for each of those containers. So in this example, the lower threshold is minus 0.05, the upper threshold is plus 0.2, and you can see this container is pretty well behaved. Its lying factor stays within the limits, nothing happens to it. But this is an interesting case. For this example, the lying factor starts at a decent plus 0.11, but as the load comes, the lying factor decreases, which means it's using more resources than what it reserved, and when it hits the lower threshold, minus 0.5, it commits suicide, meaning that it knows itself how much was reserved. It says, I'm taking more, I'm going to take responsibility, I'm going to self-terminate myself. And if you're a DevOps person, we DevOps people, we attribute a lot of problems to noisy neighbor. Anything that we cannot understand, we say it's noisy neighbor. Well, this is how you create noisy neighbors. You reserve, you tell the resource manager you're going to use these many resources, but you end up using much more than that, and you just behave like this guy. He cannot fit his own bag over there, and he's causing trouble for the neighbors as well. And vice versa, if when the load goes away, the lying factor keeps on increasing, and once again, it commits suicide, and it gets rescheduled after right sizing for the resources. This is a graph that shows the actual cores that we use versus the number of cores that we have reserved, and our auto scaling works pretty well. It's as you can see, there's a buffer between the pink and the blue, which is what we'd want to keep, and it behaves pretty well. The actual and the reserved are fairly intact. So since I have not a lot of minutes, let me quickly describe this, and then we can go to questions. So we are into indoor location as well. So what we do is we take the map of an area, and then these devices, they're moving all over the map. And what we do is we decompose the map into a grid. And then we shard the incoming location of each of these devices into multiple partitions. And what we are trying to come up is the heat map, the number of unique clients over the entire map, and basically the number of unique clients in each of these blocks. So what happens is the incoming topic is divided into, let's say, 3 partitions. You create submaps from each of these partitions, because you want to do it in a scalable way, right? When your load increases, you can, and if you can't do the unique count in one single aggregator on one single machine, you need to scale for it. So you divide it into partitions, you create these submaps, and you write these submaps back to Kafka in a different topic. And then you do a second level of aggregation where you're combining these maps into one final map. And that's the output. This is a middle school somewhere in the US, and it was interesting to see You can predict when did the school starts, where is the gate, when does it end, and it's very cool. And in future, we're planning to, joining multiple streams and do instance-aware allocation, because we use multiple type of instances from the spot market, and we've seen significant variation in, let's say, consuming Kafka. If I consume Kafka on an R3 8x large, that is significantly different from the amount of CPU it would use on a, let's say, C5 8x large. So we're planning to incorporate that into our scheduler, that we do some affinity, that certain topics get allocated on certain machines. And yeah, that's basically it. And we're open for questions. Yeah, sorry, go ahead.
So I'm a bit confused about the multi-level aggregation. So my understanding of multi-level is like you aggregate based on two attributes, right? So for example, you did at the beginning like a group by client, then each client you have some other attributes. But what you're talking is different, or I misunderstood it?
Yeah, it's if I understand the question correctly, I think what I would call what you described to me is, I would think of it as a join of multiple streams. What we are doing over here is, there is just one stream coming. So just think of it, all the people in this room, let's say we are getting their location every 1 second, and we want to know who is in which part of the room. And for whatever reason, just think that one single machine cannot handle all the 100 people sitting over here. So what you'd say is, let's create two Kafka partitions. Half of the data, let's say we are sharding on client ID, half of the data goes to partition 1, half of the data goes to partition 2, and then what would happen is, let's say his data is going to partition 1 and his data is going to partition 2, and you want to know how many people are in this region. Then he would count as 1 on partition 1, he would count as 1 on partition 2, but then you'd have to combine these two ones to know how many people are in this square over here. So that's it's the same data, but it's just partitioned into two different Kafka partitions.
Yeah. Hi. In your architecture, you had the Kafka reader, the shared memory manager, and I guess the aggregators or the processors. Those are all in one container?
Yeah.
Okay.
Yeah.
And so what was you had, the purpose was you had only wanted one reader for the topic. What was the mechanism by which the shared memory manager was communicating with the processors?
Yeah, that's a great question. And a good way of doing it is, that's point number 3. We should have just done it with Go. The problem that we are facing is, we started off, we are a startup, we wanted to get something done fairly quickly. So we implemented this in Python. And Python is not very friendly to shared memory. So Python, there is a very famous Python library, I forgot its name, but what's happening is, it's doing IPC. So the Kafka reader, the main process, reads data from Kafka, and then there is this separate process, shared memory processes, which is owned by this library. It copies data from the address space of the Kafka reader process to the address space of each of these view processes. So there's a lot of memory read and writes going over there. But yeah, if we were to use Go,
It's shared process memory is what it is? Is that what you're talking about?
So we are using a multiprocessing manager library from Python.
yeah.
On the executor, you actually had each of the processes writing the state to S3, so that's fault tolerance. But what happens if you process a Kafka message and you pass it down to the individual processes, and before they can write the state, if it gets caught, well, how do you handle that?
So in this case,
You want a mic? You want a mic?
So what we are basically doing is, this checkpointing, it happens frequently. So we have configured it for a few minutes. So suppose if before writing to checkpoint, it fails. So when the new view comes up, it picks up the old checkpoint, which is like 10 minutes old. So we are trying to minimize the duplication, but in case just before checkpointing it fails, we are just going back 10 minutes. We are not going back 1 hour or 2 hours. So it's just minimization of repetition of work.
That's the
think-
reason for the 10-minute lag that you see as well.
Yeah, and just to add to that, it's the state that you have. The state would always correspond to a Kafka offset, right? This was the state when you consumed message number 155. So that state plus the Kafka offset gets written to S3 as a single atomic operation. So let's say if you're consuming messages, its state is changing, it can change whatever it want, but whenever you checkpoint it to S3, since it's an atomic operation, when you fetch it back, yes, you might go back in time, but you won't screw up the state. If I okay. Any other questions?
What is the failure rate that you observe on the spot instances?
Well, the failure rate is, it's very, it changes. It depends on, I mean, and we've been using Spot for like 5 years now. It depends on the seasons as well. Like, for example, what I've noticed is during Black Friday, or actually a little after Black Friday, the rate is pretty high because, I don't know, there are a lot of online stores that run batch processes using Spot instances. But typically, you'd say, I'd say that typically you should see maybe 1 or 2% of machines terminating in a given day. And that's independent of the size, because the more machines you have, the more terminations. So I'd say, maybe 1 or 2%. But there will be days, like for us in March, there were days where we would recycle more than the entire data center, if that makes sense. But it doesn't happen at any given time. What you'll typically have is you have 5 machines going off now, another 5, 10 or 20 minutes later, and it's distributed over the day.
So what is the maximum data SLA that you have for like latency?
So the latency is, it varies a lot. So some of our indoor location services, they cannot have a latency of more than a few milliseconds, few hundreds of milliseconds, maybe 500 or 400 milliseconds. But a lot of our aggregated data, we can tolerate latencies of a couple of minutes without any problem. So it depends on use case. We have use cases all over the spectrum.
So do you also use reserved instances for some of your applications, or is it all spot instances?
So the only thing that runs on reserved is the Kafka brokers and Cassandra. Every microservice that we run, all the Storm, real-time processing, everything is 100% spot. Anything else? Thank you.